So today's problem is about kinetic and potential energy and converting between kinetic and potential energy, but not only that, but converting between two different types of potential energy. So at the start of the problem, we've got energy stored as a coiled spring. That energy is converted into kinetic energy and then back into gravitational potential energy. So we've got a 2 kilogram. So this is question 740 from Young and Freedman. We've got a 2 kilogram block. It's pushed against the spring with negligible mass and a force constant of 400 newtons per meter, and it's compressed by 0.22 meters. So when the block is released, it moves along a frictionless horizontal surface and then up a frictionless incline with a slope of 37 degrees. What is the speed of the block as it slides along the horizontal surface after leaving the spring? That's the first part. So we convert our potential to kinetic energy in the first part of the problem, and we want to figure out what's the velocity of the block once that conversion is done. And then when that kinetic energy is transferred back into gravitational potential energy, what is the height reached by the block as it goes up that incline. Alright, so let's get on with the problem then. So we'll make our image small here, and then the first part of the problem we're converting a potential energy in a spring to kinetic energy. So the formula we need for the potential energy stored in a coiled spring is a half k x squared. So k is the force constant of the spring, and x is basically how much we're compressing that spring by from its equilibrium position. And that's all converted into kinetic energy, and the kinetic energy is a half mv squared. So we know that the force constant of the spring is 400 newtons per meter. We know that x, the amount by which the spring is compressed, is 0.22 meters. So from there then we can work out the initial potential energy, and we can solve. So we also know that the block weighs 2 kilos, and that gives us everything we need then to only have one unknown left. So we can say then that v is equal to the square root of k over m times x. And the square root of k over m times x, we have k, we have m, and we have x. So we get the square root of 400 newtons per meter. 400 newtons per meter over the mass is 2 kilos. And then we multiply that by the compression, or how much we're moving the spring from its equilibrium position, and that's 0.22 meters, and that's multiplied on the outside, and that gives us 3.11 meters per second. So when we convert that stored potential energy in the coiled spring into kinetic energy, and the block moves along the frictionless horizontal surface, it's going to do so with a velocity of 3.11 meters per second. It's not going to slow down because the block is frictionless, or it's not going to slow down on the horizontal part at least. And then when it hits the slope that we see in the diagram which the publishers have given us, it's going to slow down only because of the kinetic energy being changed into potential energy rather than any friction. So the second part of the problem now is, how do we figure out, how is that kinetic energy that we've given the block converted into gravitational potential energy, and how can we calculate that the height that the block is going to go to before it stops from that potential energy. Okay, so I'll just label my parts here. So that was part A. Now part B, we'll draw in a little diagram here to set the question up for ourselves. So this is our frictionless slope here, and we'll call this distance here y. So y is how far in height the block goes before it runs out of steam, if you like, and starts to roll back down again. So the block is moving in this direction. So let's call the length of this side, or the length that the block moves before it stops, L. So now what we want to find out is, what is the potential energy of the block at the point where it stops? And that potential energy is going to be equal to, so EP is going to be equal to mg y in this case. So mgy is the mass of the block times the acceleration due to gravity times y, which is the height it's reached when it runs out of steam, if you like. So what's y? Well, if we do a bit of trigonometry, then we can state that y is equal to, EP now is equal to mg. If this is the angle theta, so let's call this angle theta here, then y, which we have on the right hand side, we can solve for, is going to be equal to L sine theta. So now we have the potential energy of the block. So there's two ways of going about solving this problem. you could say that in one way. So so the block starts, say, over here, and it's attached to the spring, and the spring is coiled. So we've changed that initial potential energy of the block into kinetic energy and back to potential energy again. But the key thing here is at no point has the total energy of the block changed. So if we want to find out what the gravitational potential energy is, on the right hand side when the block reaches the top of its journey, that's going to be the same value of potential energy as we had here. So we can equate those two potential energies and solve for the height from there. We could also take what the kinetic energy of the block is as it's sliding along, and then convert that into gravitational potential energy. And what we'd find is that we get the same answer, but we'll do it in terms of potential energy. So the half kx squared, which was the potential energy of the block as it was sitting on the coiled spring before we let it go, is going to be equal to mg L sine theta. So y is equal to L sine theta. So if we solve for L now, which is actually what we're looking for in the problem, I believe. So let's go back and just double check exactly what we're asked for. So we're asked, how far does the block travel up the incline before starting to slide back again? So it's asking us for what we've denoted as L here. So we know that, when it reaches its maximum point, it's going to have a certain height, if you like, y, and we can relate that height y to L by the little bit of trigonometry that we did a minute ago. So those two potential energies now are equated, and from there then we can solve for L. So L is what we're looking to solve for. So we go L equals a half kx squared, so we're just manipulating this equation here, divided by now what has happened there, mg sine theta. So now this is just a plugging in the numbers problem. So we've got a half times the spring constant is 400 newtons per meter times x squared. So our x now was the compression of the spring, remember that? So that's minus 0.220 meters. That's going to be squared. And we're going to divide by m, which was the mass of the block, which was 2 kilograms. G is 9.8 meters per second squared. And sine theta is going to be sine 37 degrees. And when we calculate all that out, we get 0.821 meters. So the second part of the question asked us, how far along the incline does the block slide? So I actually thought when I first started solving this problem that it was asking us for the height that the block achieved, which I think I may have said at the start of the video. But in fact, what it's asking us for is how long along the incline it slides. And when we do that calculation, we get 0.821 meters. We could have just as easily here, if I put this in red, we could have said half mv squared equals mg L sine theta, and taken the mass of the block and the velocity we got from the last part. And what you would have found was that you get exactly the same answer. And the reason for that is that the total energy of the block doesn't change. It goes from all potential energy when the spring is stored to all kinetic energy when the block is moving to all potential energy when the block is stopped and just about to turn around as it slides up here.